All right, welcome back. So far we have assumed the following things about fluids, right? We have assumed that fluids fill the shape of their container, that their density is uniform throughout a fluid, and that the fluids are not flowing. And so this critical assumption is one that we are about to change. We're going to start talking about fluids actually flowing through different devices. We're moving towards an understanding and a more realistic understanding of fluids, about how the volume of a container, the velocity, and the flow rate change as different components of a fluid flowing through a system change. And so the really fun thing about this is that you know just from life experiences how fluids work. You just haven't put the math to it yet. And so any 5-year-old knows that if you decrease the volume if you decrease the area at the end of the hose, what happens to the water coming out at the end? Right? It goes faster. And kids always have a lot of fun with this. And so anytime you put your thumb over the end of a hose, you're decreasing the area and thus increasing the speed of that fluid, which also means in projectile motion that fluid can go farther. Or you can just give your friend a good prank. Fluids flowing also has to do with a lot of other practical situations. You just might never have known it. And so when we've got air that is flowing over something, right, we get these things called contour lines. And when contour lines get squeezed together, that tells us that the velocity of a fluid is increasing. And so what we see with like an airplane wing or an airfoil is that we have increased velocity over the top, which causes a decrease in pressure. And we'll learn about that a little bit more later. But that decrease in pressure is what allows that wing to lift up and what allows that plane to fly. Another great example, cars are generally shaped like an airfoil, and so where these contour lines are getting closer together, that fluid is speeding up. Thus, the pressure is decreasing, and we get an uplift in the car. You don't really feel this at normal speeds, but for racetracks and things like that, going very, very high speeds, the car actually does kind of lift up, just like an airplane wing, off of the pavement. And so what we see in a lot of racing cars is that they put a little spoiler on the back, and that little spoiler, again, speeds up air underneath, right? Decreases that pressure, and we get a downforce from that spoiler to keep the car in contact with the pavement. It has to do with how we get water from our waterworks to our house. And so generally under our main streets we've got a very large pipe that then divvies up into very, very small pipes, right, going into houses. If you've ever lived in a house that has low water pressure, oftentimes it's because of this. In some situations in a town like Rangeley, we also have to change the pressure and the velocity of the water to get it up over hills, and we'll talk about that here in just a minute and how people are able to do that. And then I think the coolest application of all of this is that your blood actually is a fluid, and it flows through many, many different kinds of containing devices in your body. So you've got veins and capillaries and arteries, all kinds of stuff that change size as they go throughout your body. The other way that things can change size, right, is when you have an unhealthy diet and you get a buildup of plaque in those arteries. That decreases the overall area through which blood can flow, and you end up with high blood pressure because of this. And the high blood pressure has to do with having this very large area going to a very small area, and it kind of you can think about it as kind of like backing up, and your heart has to push a little bit harder to get that fluid through the smaller area. And so these are all really neat applications about how fluid goes through and changes, the size of the container through which it's flowing. So here's some assumptions that we're going to make. We're going to assume that the fluid is incompressible, and water is a great example of this. We're going to assume that the flow is steady, and so we are going to give, I think, an example with a heart here, but what you need to know is that, the flow of blood through your body is not actually steady because of the way that your heart beats. But for the purpose of our examples, we're going to assume that it is steady. And then this is a big assumption which we're going to change in 13.7, but we're going to assume that fluid flows easily and it is non-viscous, which means it doesn't have any kind of a friction or a thickness to it. right? And so, like I said before, I love this example because it's something that we've all done. When you decrease the area, right, at the end of a hose, right, by putting your thumb over it, what you get is a higher velocity out of that. The thing 5-year-olds don't know about this is the mathematical equation for it. And so what we talk about when we talk about fluids is flow rate, which we're going to represent by the variable Q. And then there's this equation of continuity. And the equation of continuity says that the flow rate is equal to the volume of water that is passing through per time. And we usually talk about this in terms of cubic meters per second. We can also calculate the flow rate as the velocity vector times the cross-sectional area of the device that it's flowing through. And we know that if flow rate is steady, then the initial flow rate is going to be equal to the final flow rate. And so what we see is that if the initial flow rate is equal to the final flow rate, then these statements are also true. And so I know initial flow is equal to final flow because of that assumption. I know that I can calculate flow rate as velocity times area. And I know that I can also talk about it in terms of volume, right? This is volume, typically in meters cubed, volume per amount of time. Now, you're going to see this in a few things that we do. We've already used the variable Q. When I do my own calculations, I put a little strike through it so that I know I'm talking about flow rate and not heat transfer. If you choose to do that, that's up to you, but that's just a little way that I differentiate between the two. Alright, so for example, the large pipes under a city street have a radius of 1.5 meters, right? 1.5 meters. And through these water flows at a speed, a velocity of 0.5 meters per second. Pipes that branch off of this main line have a radius of 0.5 meters. 0.5 meters. At what speed does water flow through these? Right. And so because of the continuity principle, I know that the initial velocity and area has to be equal to the final velocity and area. I know that the initial velocity, the initial velocity is 0.5 meters per second, and the cross-sectional area is going to be pi times the radius squared, and in this case that's 1.5 meters squared, is equal to the final velocity, whatever that is, times the area, which again is going to be pi times 0.5 squared, which should give me a final velocity of 4.5 meters per second. And this makes sense per what we already know, that as the area decreases, then the velocity must increase. And so what I want you to do is go ahead and try number 29. Alright, so if you haven't already, go ahead and pause the video and try number 29 on your own. I'm going to go ahead and start working through it. So it says the River Pascal, with a volume flow of 500,000 liters per second, joined with the River Archimedes, which flows at 1 million liters per second to form the Bernoulli River. If the Bernoulli River is 150 meters wide and 10 meters deep, what is the speed of the water? And so the first conversion that we need to do is that 1 liter is equal to 10 to the negative third cubic meters, and cubic meters is what we want. And just to give you a visual here, we've got two rivers, right, that are kind of flowing into one river. And we've got the River Pascal and the River Archimedes that come together to make the Bernoulli River. And so once we get this conversion, we know that the flow rate of the Pascal plus the flow rate of the Archimedes is going to equal the flow rate of the Bernoulli River. And so the first thing that we need to do is get these values from liters per second to meters cubed per second, which is going to give us a rate of 500 500 meters cubed per second. Boop, boop, boop. And 1,000, right, 1,000 meters cubed per second. Good. And now we can plug those values in down here. And so the river Archimedes is 500 meters cubed per second. And the river Pascal is 1,000 meters cubed per second. And we also know, right, these have a combined flow rate of 1,500 meters cubed per second. We know that's going to equal the flow rate of the Bernoulli River, and we know that we can find the flow rate of the Bernoulli River by the velocity of the fluid times the area. Now we're going to assume something really funny here. We're going to assume that the Bernoulli River is a square river. And it's got a depth of 10 meters and it's 150 meters wide. This is a decent approximation. And so that's going to give us an area of 1,500 square meters. And so then I'm going to come down here. The velocity is what I'm looking for. I know this has an area of 1,500 square meters, and that's equal to 1,500 cubic meters per second, which is going to give me a velocity of 1 meter per second. And then I'm going to evaluate this and say, okay, well, does it make sense that the water is flowing slower in a wider river? And yes, it does make sense that two smaller rivers would be flowing very fast, and as soon as they open up into that bigger area, they flow a little bit slower. Alright, and so this leads us to the idea, right, and we've kind of got a few ideas now, that with a very large area, something has a low velocity, and with a very small area right here, we find high velocities. Right, and so we know this. We also know that as the velocity of a fluid increases, our pressure is going to decrease. And so where we see this increase in a velocity, we see a low pressure. Consequently, when we have a low velocity, we see a high pressure. Right. And when I take this information about pressure and I combine it with what I already know, that force equals pressure times area, or I'm sorry, pressure times area, then I also know that right here I'm seeing a very low force, and I see very high forces where I see my high pressure. And if you think about it, it makes sense, right? And so if you're going to get hit with some water, would you prefer it be a very small area at a high velocity, or a very large area at a low velocity? And you can think about this as getting hit with waves, and obviously the bigger one is going to have higher pressure and it's going to have a higher force. And so if you have a choice, you want to get hit by something small because of the low pressure and the low force. And all of this information leads us to Bernoulli's principle, that we see low velocity with the high area, and that accompanies with high pressure and force. And we see that the inverse is true over in the smaller areas, that we get a very high there we go, velocity and low pressures and force in those areas. And ultimately, all of this leads us to a mathematical understanding of Bernoulli's principle. And what Bernoulli's principle says is that, you know, if I've got a pipe with some kind of fluid going through it, that pipe is going uphill or downhill and kind of changing surface areas, I know from our previous chapter that energy is going to be conserved. And so I can say, right, that in the initial problem, or in the initial stages, that the pressure, the kinetic energy, and the potential energy are ultimately going to be equal to the final pressure, kinetic energy, and potential energy, okay? And when I expand this formula down, it actually does look kind of scary, but don't be intimidated by it. And so what I see is that pressure here, right, the initial pressure plus 1/2 of the density, and just like I do with flow rate, I